Mr. Fredrick Heintz from Linköping University. He's director of the graduate school for the Wallenberg AI Autonomous Systems and Software Program, the president of the Swedish AI Society, researcher at the AI Sustainability Center, and a member of the European Commission high-level expert group on AI. He will give keynote speech on fairness, explainability, and trustworthiness AI, technical challenges and state of the art. Mr. Heintz, are you ready?
Oh, yes.
Okay, please.
Oh, yes, it works. I was just trying to get a new microphone since I'm one of those people who try to move around and just get stuck behind a podium like that. You cannot move anywhere, so that's why I changed the microphone. Sorry about that. Yes, so it's a great pleasure to be here. Thank you very much for the invitation. It's my first time here in Seoul, and I really enjoy it so far. So what I wanted to talk about today is to actually dive in a little bit into those discussions or the kind of topics that we have been discussing in the morning session around fairness and explainability. And so actually what I wanted to start with, since I've been involved in this European Union high-level expert group on AI, was to say just a few words about the work that we have been doing. And actually it continues on what we have been discussing before, namely the need for trustworthy AI. I mean, I personally believe that we are kind of at the inflection point where if people don't trust these systems, we will have a huge uphill battle to do in order to regain the trust of users, citizens, and so on. So I really think it's important, both from a company perspective, but also from a government perspective, to build systems that people can trust in, because that's the best way to get people to use the systems, so that we can get people to get to leverage the benefits of these systems. So basically, the approach that we've been taking in Europe is very much that we're not interested in participating in any race. We're more interested in trying to find a way that's in line with the way that we have been working, which means that we are a truly multicultural place. We have many different countries working together. We have many different languages and so on that we need to take into consideration. So for us it was very natural to take the perspective of a human-centric view, that AI should not be an ends of its own, but a means to achieve the ends. And we want these systems to really benefit people and work for the good of people. And in order to do that, we have to be able to trust them, so they have to be trustworthy. So that's kind of the work we've been doing in this high-level expert group. That's too much. So in order for an AI system to be trustworthy, we said it needs to satisfy three requirements. It has to be legal in the sense that it has to apply to the particular regulatory frameworks that are applicable in this particular case, which I would actually argue in some cases will be a challenge. I mean, for example, assume you have an autonomous car driving around, and you basically have the choice of either breaking the law or risk being in an accident. Can you, as a provider of an autonomous car, kind of program your system so that in some cases it will actually break the law? And I think it might be hard to argue, because I mean, assume that it broke the law, there were no accident, and you broke the law. Yeah, but there was a risk of accident, but there were no accident. So you cannot come in a situation that's really tricky to get out of. The second thing is that these systems have to be ethical, and in our case it means that it has to adhere to four ethical principles that we have defined. And finally, which I haven't really seen in any other similar frameworks, and that is that the system also has to be robust. Which means that you can have the best intentions in the world, you can strive to reach all the principles you want, but if you have a bad implementation, it's still a crappy system. So I mean, you really need to make sure that your system is safe, secure, and robustly implemented. Otherwise, it doesn't really make a difference if you're also very ethical and legal and so on. So I think that's a very important addition. So what are then the ethical principles that we've been working along? So the first one is this respect for human autonomy. And what we see today is that there is a tendency that humans basically lose their autonomy in the sense that just do whatever the machine is telling them to do. And so on, that you as a human have the right to an agency. You should make your own decisions on your own grounds, and that's something that we need to protect. Prevention of harm, of course, the system should not cause harm, should work to avoid that. Fairness, which I'm talking more about, and explicability, which in some sense is a more general term than just explainability. It also relates to transparency and accountability and so on. So basically that we as humans should understand how the system works and why it does what it does, and that we should be able to contest it if necessary. So based on these 4 principles, we also then define 7 requirements. Actually, we try to take the step beyond just defining the principles. In some sense, you could say it's relatively easy to come up with the principles. The really tricky part is how do you actually operationalize this? How do you realize it? How do you implement it? How do you get the system to actually live up to these principles? That's a much harder challenge. And we have taken actually 2 steps in this direction. One step is that we have defined 7 requirements, and the second step that we also started to make an assessment list, which I think had like 133 something different questions that you could ask yourself in order to start verifying whether you live up to these requirements or not. So this assessment list is actually something that we will continue working on during the fall here through a piloting project. So that was just quickly about the work we have been doing there in the EU. So what I wanted to talk about now is, of course, these concepts of fairness and explainability. And when it comes to fairness, I think it's a good place to start when it comes to bias. So, of course, all these systems are data-driven to a very large extent. And then you're going to run into challenges based on what data you use to build your systems. And what we realize is that there are several different types of biases that may occur. In some sense, the most obvious one is that the training data set that you use do not really represent reality. We have seen the cases, for example, with these facial recognition systems, as has been mentioned in the morning, which worked very well on white males, but it worked very less well on colored people, and especially colored women. And then they started to look into this, and they found out basically the developers had mainly used themselves to generate the training data and to train the system. And of course, that's a simple example where the data set you use do not represent reality. In a sense, that's easier to fix, just to collect more data that's more representative of reality. A much trickier case is where there have been examples, for example, with the systems providing ads for jobs, where it turned out that men were more likely to get an ad for a higher paying job, while women were more likely to get an ad for lower paying jobs. And again, if you look into why this was the case, it turned out that it basically looked at this statistical data. And women were more likely to have these lower paying jobs today. And the men were more likely to have the higher paying jobs today. So the system was basically reproducing reality as it was, or yeah, as is. And in some sense, it actually captured reality. And this was a case where we actually we do not want to replicate reality. As Professor Mulligan was saying in the panel, that if we want to replicate the past, yeah, these systems work very well. But if we want to change the future, then we need to do some intervention. And then actually that's a much trickier question, because then the question becomes, who has the authority to make these normative decisions on how to change the training data? If it's the company that does this, if it's a commercial product, they of course run the risk of making a normative statement that other people don't agree with. and so on. And of course, if the government is doing it, again, that becomes a challenge. So those are two examples. We also have other types of bias, like interaction bias, where the system is being interacted with by people who basically act in order to make the system to do bad things or to work against the system. So we saw this example from Microsoft with this Tay chatbot, which people were saying rude and nasty things to it, and then it became learned from the people interacting with it to, oh, people probably like to be talked in this way, and then it behaved in the same manner. And again, this is a situation that we would like to avoid. So there are a number of challenges when it comes to these data-driven approaches. Let's see. Probably too much is. It's delayed effect, and that's become hard to make a decision. Anyway, now we kind of come to, so what is then fairness and this fairness-aware machine learning? So fairness in general can be defined as just impartial and just treatment of behavior without favoritism or discrimination. So in some sense, everyone has an intuitive feeling of what fairness means. And I think this definition probably captured that fairly well. The challenge, as with all these definitions, is how do we turn this into something that can actually be implemented in a computer? How to actually translate this common sense statement into a precise technical statement. And that is a major challenge. But then what we try to achieve then with this fairness-aware machine learning is then to develop algorithms to provide methods under which the predicted outcome of classifiers operating on data about people is fair or non-discriminatory. But just as one simple example of what do we mean by fairness, I think this comic illustrates as well. Do we want equality, basically giving everyone equal amount of resources or equal opportunity? But if you have very different characteristics, then you might not really get a good outcome. Or is it more equity, trying to get the same result? So everyone should have the same outcome rather than the same amount of resources. And in this particular case, you see that by redistributing the resources, everyone can get the same outcome. And of course, these have very different properties and very different end results. So this shows the challenges involved. So actually, I found this kind of decision tree for fairness from the University of Chicago, which actually set up a number of questions one can answer or ask themselves and answer in order to find out, in this particular case, 6 different types of fairness. So the first question here is, do you want to be fair based on disparate representations or based on disparate errors of your system? Should you focus then on the errors, the mistakes, or should you focus on how well it captures something, represents something? Well, let's go for the representation. And then the next question becomes, do you need to select equal number of people from each group, or should it be proportional to their percentage in the overall population? So here the challenge becomes, do you have a population where the different groups are roughly the same size? Then, of course, the first one becomes better, that you can select equal number from each group. But you might have the case where, for example, you have a minority is much, much smaller than the majority group. And then if you then select the same number for both, it will be very different properties, statistical properties. So here you have to make the choice. If you choose the equal number from all the categories, then you have the concept of equal parity. And this is also known as demographic or statistical parity, which is very commonly used. If you rather take the proportional, then we get proportional parity instead, which is then equivalent to disparate impact. And then we can go down and start to look at errors instead, and then the question becomes, are your interventions positive or associative, or assistive, sorry, punitive or assistive? And if they're punitive, which means they could hurt individuals, then the second question is, are you intervening with a very small percentage of the populations? Yes or no, and so on. So you see that starting to define a large variety of different fairness measures can start to get quite tricky. And there's even a theorem basically stating that these are incomparable. So it's not like one is a subset of the other, but actually you have to choose which one you want to achieve. So here you have to make a choice based on which type of fairness you want. Let's see. Sooner or later. So when it comes to the question of how to actually achieve this fairness, what we see is that there's been a very dramatic increase in the research literature in this area. So this area of fairness has become very popular with a large number of publications in the last couple of years. So of course I will not go through a large number of them, or what I will try to do is just give a sense of different types of methods that you can use. So basically, you can very simplified depiction a system like this. You have your data, which you use to train your system, and then of course you have the data that when you run the system, which then generates the decisions. So the first type of approach is to use a pre-processing approach, where you have your data, you run it through this pre-processing functionality, and then you get a new data set which should then be more fair or have the desired properties that you want. And here we can see that there are a number of different approaches, like reweighing, so basically changing the weight of the different training samples, optimize pre-processing, basically trying to change the distribution. So the kind of distribution you had before, you generate a new distribution that better captures the properties that you want. You can even use learning to basically set up like a latent variables that you want to capture the data without the particular discriminatory features that you may have. And then you learn this latent representation and use this latent representation instead of your original representations. And so on. And you can try to remove things that causes this discrimination. And there's one thing I should say also, that one very simple way that some people are using is that you remove all features from your training data which can be associated with some discriminatory factor, for example, sex or age or religion or things like that. The challenge, however, is that usually these are highly correlated with other variables that you might have. For example, if you have the first name of the person, at least in Sweden, you can basically very high probability estimate what is the sex of a person based on the first name. From the last name, sometimes you can deduce what is the religion of a person because it's highly correlated, and so on. So usually it's very hard to just take away a few of the features and there get a data set which does not contain these potentially discriminatory factors. So that's important to keep in mind. The second approach is, of course, to try to adapt or change the kind of algorithms that you use. So you change the particular algorithms. So you can use something called adversarial debiasing, or you can use prejudice removal, so basically removing things that would be prejudiced. And the final type is then to do processing. So basically, you get your decision from the system, and then you look at these decisions and try to improve them, removing discriminatory cases, for example. So you can equalize the odds through post-processing. You can also do this in a more calibrated sense. Again, this is basically just doing a linear model. Here you can use machine learning to improve it even further. And you can also just reject things that would be unwanted. So basically there are a number of different types of ways of dealing with this fairness in your system. So when you try to do this, you first of all, of course, have to decide what is the type of fairness measurement that we want, what is that we want to achieve, and then you can select different types of approaches based on that. Oh, sorry. So that takes us to explainability, which I think from a technical point of view, I think is in some sense more interesting. We have had some interesting comments here earlier today about why should we have explainability in this question of explainability versus accuracy. And I would argue that I think that I would say it's very unlikely that you have a highly accurate system that you cannot understand at all. And I think probably the challenge there is that accuracy is, you believe the accuracy is very high. So the question is, of course, then becomes how you have validated the system and how you have really convinced yourself that this accuracy is true. It might work very well for a particular system that you have, a particular validation procedure you have, but the question is, how does it go beyond that? And actually, I think this explainability is also interesting because it will allow us to understand the limitations of the system and why would it work, why wouldn't it work with slightly different populations. So I do think that explanations are very interesting. I also, to a large degree, agree with this, that those that question why we always need explanations. And actually the reason there is because we as humans are quite poor at giving explanations. I mean, most of the cases we cannot always explain how we do things or why we do things. So I think it's also to have a kind of a balance between what we expect from people and what we expect from these computerized systems. Anyway, the Oxford Dictionary definition of explanation is a statement or account that makes something clear. So basically that's the purpose of these explanations, so to better understand the things. When you look at explainability, I found a number of definitions. So for example, one is the ability to explain or present in understandable terms to a human. So basically here, the purpose is that you want to make a person, a human, understand something. And actually I think this is key to this term of explainability because, and actually relates to what Professor Mulligan was talking about, namely this contestability. Because I mean, in many of the cases where we use this kind of system and where this, the purpose of an explanation becomes valuable is, for example, you have a decision and that decision might go against you. And then in some sense, you may not be that interested in why the system made that decision. What's more interesting is what can I do about it? And in some sense that usually boils down to what are the kind of factors that algorithm or decision-making procedure triggered on, which led to the fact that you got a negative result. So I think this understanding well enough in order to challenge it is a key thing here. I also think this is to some degree related to transparency, that we see a lot that in some sense we could present a lot of the details about a system. I mean, it could be the case that you actually have access to the full system. You have access to the training algorithms, the data and so on. But to most people that would be completely useless because we wouldn't understand what it means or how to affect the outcome of that. So I actually think the purpose of explanations is also to generate abstractions, to abstract away a lot of the details in order for humans to understand why the system is doing as it's doing. So I think there are many different usages of explanations, and that's probably also why it can sometimes be tricky. And then we have DARPA, who has a large program on explainable AI, and there they define as AI systems that can explain the rationale to a human user, characterize their strengths and weaknesses, and convey an understanding of how they will behave in the future. So here it's a lot of different aspects that is important. And if we continue on that trend, if we're looking at this DARPA XAI program, basically if you look at the kind of traditional way, you have your learned system and you have a user which interacts with this, but usually the user has no way of inquiring, like why did you do that, how does it work, when will you succeed, when will you fail, and so on. So understand it more. So the idea is then to build either explainable models or explanation interfaces which the user can then interact with instead of interacting with the models directly. So the purpose is then to provide explanations for individual decisions, enable the understanding of overall strengths and weaknesses, convey an understanding of how the system will behave in the future. So I think this is also very important, that you want to have some predictability so that you as a user know what should I do in order to get a certain result. And actually this kind of way, if you have a better way of explaining why the system made certain decisions, it also helps the developer in improving the system over time. So it actually facilitates the continual development of the system. So if we look at a number of different approaches, so today we use a wide variety of different types of machine learning approaches. We have kind of more, say, a bit more traditional, like decision trees and random forests. They usually have a higher degree of explainability, but also usually have a lower degree of accuracy. While on the kind of other end of the spectrum, we have deep neural networks, which tend to have a high prediction accuracy, but usually have a low explainability in the sense, I mean, again, this is one of those things that I find interesting, because in one sense it's just a mathematical function. The challenge is, of course, that it's a number of millions, maybe even a billion parameters, and we humans are just really poor at understanding that 1 billion parameters. It's not like you cannot explain it. I mean, in some sense it's just mathematical fact. It's just that we don't understand it. And I think that's another interesting question here, in the sense that what can be understood and at what level can we understand it. So again, what I think is really important is to make these abstractions. And what we humans normally abstract is in form of symbols, and we have meanings associated with the symbols, and that allows us to understand things. So actually that's what I think about the future there. So well, of course one way to do is to generate explanations from these models. So you take a model that you cannot really understand and you generate explanations of it. So basically having the explanation and the prediction system running in parallel. The second approach is to have models that are easier to understand. So instead of having separate model for prediction and model for explanation, you try to improve the model so that you maintain the accuracy, but you improve the explainability. Or a third approach is basically that you can induce the model from the data. So in some sense, what we want, or what this program wants to do, is that we want to maintain the accuracy but improve the explainability. So this is then some of those techniques. So this LIME is one concrete example of doing this. So basically you have images that have been, or to classifier trained on images, it's do super pixel segmentation, and then it kind of grays out some of these superpixels and then tries to see what is the accuracy of the prediction, and then build a locally weighted model on this, and then to find what are the superpixel which kind of generates most of the probability of this image being classified, and that in some sense is used as an explanation. So this is one common model that's being used. Yeah, we had this question of the right for the right reason, and then I had to pull down some data. Right for the wrong reason. It's actually related to this accuracy question as well. So this was a paper presented at ACL earlier this summer. So basically what they were doing was evaluating a number of natural language processing systems able to answer queries. So basically you were given a natural language statement, and then another natural language statement, and you want to determine whether the second statement is entailed by the first one or not, the logical conclusion of the first one. And what they found is that even in these state-of-the-art systems, they basically use 3 different very simple heuristics, like lexical overlap. So basically if the words used in the query is part of the sentence, that's, then they say yes, it's entailed from that, which of course we know is trivially false, because you could just add a not, and that's the case. So actually it was the case that David mentioned in the case where it is added, have you been leader of a group with at least 10 employees, and they just add 10 and then you were said yes. And so on. So they found a number of very simple heuristics. And why I thought it was interesting in this discussion around accuracy is because the accuracy in the case where the question was positive, so when the second statement was actually entailed by the first statement, was really, really high. So their accuracy was really, really good. But if you took all the cases where the second sentence was not entailed by the first, the accuracy was really, really poor. And probably the validation set here contained a lot of cases where it was true and few cases where it was false. So therefore the overall accuracy of the system was very high. But that does not say that the system actually was accurate. It was only accurate on the positive cases and not on negative cases. So I think this is a cautionary tale when it comes to accuracy, was my point of this particular slide. And I will jump over some stuff, if I can. Oh, so this is probably good to end, place to end. So my personal view is that I think we need to move away from these correlation-based approaches and to move more into causality-based models. Actually, we've heard that mentioned in the morning session, because data itself, in some sense, will not tell you the story unless you have your assumptions on how this data, the variables in the data relate to each other. And this is given by a causal model. And if you have a causal model which captures your assumptions or your theory about how things work, then that allows you to interpret this data in a much better way. I also believe that we need to be integrating more purely data-driven approaches, which are very popular at the moment, with more knowledge-based or reasoning-based approaches, which can also leverage all the prior knowledge that we have. And I think that we can use these causal models both to explain the past or explain particular data that we have, and can be used to predict into the future much better than if you just have the correlation. So that's what I'm personally working on, this kind of general framework. Yeah, we have a large research program in Sweden which also works on these questions. So the final result here, so of course we heard a lot about AI. I actually got the question at the lunch what I think is kind of the goal of AI. Personally, I think the goal of AI is really to understand what is intelligence. We want to understand what this thing called intelligence really is, and then we want to understand it well enough to actually be able to implement it into computers and so on. So I think that's very interesting. And then of course this will affect all aspects of society, and this means that trust will be absolutely central. I would say that, I said in the beginning that I think people are starting to lose trust in this kind of digital systems. Looking at least from a Swedish perspective, it seems that people are starting to lose trust in society as a whole. It's not just the digital tools that we use, but society. And therefore I think this is one very important cornerstone to regain and to maintain this trust. As said, from a European perspective, we have defined trustworthy AI systems as legal, ethical, and robust. I talked about fairness, and I think in some sense the key point here is that there are many ways of defining this technically, and of course to work towards it. And the same with explainability. Again, there are many ways to technically define this. So I think these are examples of two concepts that are needs to be more refined. We need to understand how they are used in different contexts. They need to be used in a situation-dependent manner. So I don't believe that there would be like a single solution that solves all cases. And of course, this is a very active and fertile research area. Another thing that I think is very interesting here is that it's not a purely technical question. I mean, from a technical perspective, you can in some sense find, can we develop a better machine learning algorithm that better captures whatever representation we have, but it doesn't say which representation do we want to capture. So I really think that we need to work in an interdisciplinary way in order to address these things. So I've been starting to work with actually people from law to work on this, on transparency is that particular project. We haven't started yet, but we will do. So I think for people interested in looking for research problems, I think this is a very good area. And what I also think is interesting is that I think that by studying how to make better decisions, we will help people make better decisions, because we as humans are, I would say, as unfair and unjust and so on, and prejudiced and all these things. So it's not just the computer systems that are behaving that way. It's us as well. And I think that by studying how to make better decision making, we will improve human decision making as well. And we will start to look at how do the courts make the decision? Are they really being fair in these kind of different notions? And so on. So I actually think it will have a huge positive influence, not only in the area of machine learning, AI, and computer science, but in society as a whole. Thank you very much.